All right, good morning. First thing is to adjust the volume because I know I'm more on the louder side of those speakers, and here we go. So thank you for stopping by. Not as many people as yesterday, but nevertheless, so we have a more intimate session here. It's about latency. So, and I choose that particular line, your flight will be delayed, because that's what we experience day by day these days. Well, not by 20 milliseconds. We would be lucky if our flight would only be delayed by 20 milliseconds, right? And for audio, this is already quite a big number, as you will see throughout the presentation. So it was just a randomly chosen number here anyway. All right, so let's jump into it. I don't have to introduce myself again, so I jump over here. Latency. So what is latency? Well, if we ask Wikipedia, we got the answer that latency is a time delay between the cause and the effect of some physical change in the system being observed. Well, and further, if we read further, we see it's a latency is a consequence of the limited velocity, basically, which always has to be. Is that me? My voice? No, cracking up. The voice is cracking up. Which is always less than the speed of light. So these are the information Wikipedia provides. How does that apply to audio technology, to video technology? Well, if we look at the traditional signal distribution, we have AES, MADI, analog lines, we have SDI lines on fiber, and well, those basically are used in traditional setups as we know them. Here's as an example a live setup. We have a stadium, an audio router, mixer, and then a transmission chain in the back. And basically, what all this is about is it's a fixed connection between, if we look at a particular microphone, it's a fixed connection between the microphone and its destination, right? So even if we have a routing system in between, we establish a fixed connection from source to endpoint. And that is what we call a circuit-switched routing system. Because at the end, we always establish circuitries, right? And the benefit of this is we have fixed and deterministic latency. We always know we feed something in, and at a determinal latency, usually just a few samples or even less, we get the signal out of the system. If you ever wondered where circuit-switched routing comes from, here's the answer. That is circuit-switched routing. And this is being used all the time, even nowadays, in analog or digital routing systems. So, what's the latency in these systems? Well, basically, the factor is the speed of light. If we look at the speed of light and some travel times, well, we all know that with the speed of light, we have 3.3 microseconds at 1 kilometer distance. So that is far beyond what we use in studios and these kind of things. So we can neglect latency simply, right? In most cases, at least. And even if we go to the moon, we know we have 2.6 seconds travel time, latency coming back and forth. And radio waves, this is also a fixed and determinable latency. And we have some other fun numbers down there, which I don't want to explain. But what we are looking at right now is network media distribution. And with network media distribution, things really change. Network media distribution translates into packet switching. And why is it called packet switching? Well, similar to circuit switching, this is packet switching. And this is actually what networking is about. It's packet switching. Now, if we look at a typical network, a mesh network, we see a particular sender, particular receiver, and we have a number of switches, routers, network transporting equipment in between. And the idea is just with DHL or FedEx, we have content and we have to wrap the content and send the content through the network. And that packet has an address, and the network exactly knows, okay, I have to distribute the content to a particular destination. So a particular route is being picked in a network, and if I send off another packet, it may happen that this packet takes its own different route from the previous packet. That doesn't apply to our local area networks, but in a mesh, wide area network, this could well be the case that we have even different routes on a particular connection. Well, when we have different routes, the problem is we don't have a fixed connection anymore. It's not a switched circuit anymore. And consequently, we don't have a deterministic latency anymore. The latency may vary depending on how and where a particular packet is being routed. So, what are the determining factors for network-based media distribution? There's a number of effects coming in. It's not just the speed of light anymore. So first of all, the underlying network technology itself is a determining factor. How's that? Well, easy as that. We know fast Ethernet, 100 megabit per second networks. More common these days is gigabit networks, which have 1 gigabit per second transport speed. But in professional installations, we can see everything up to 100 gigabit per second and even 400 gigabit per second is available as technology. And as you can see on the far right column, the transmission time of a particular packet, given that it's filled to its maximum size, it can be transported, of course, directly relates to the speed of the network. So, while we have 25 microseconds of transport delay per switch or per hop in a 1 gigabit network, it's just a tenth of that in a 10 gigabit network. So, rule of thumb, first thing to remember, we are talking a 1 gigabit network. We will have about 1 sample time of transport delay per switch, based on the switching technology and the way things are forwarded in a switch. So that's one thing to remember. Doesn't sound much, but that is there. If we have 7 switches in a row, we will have 7 samples of delay as a rule of thumb, just because of the technology. If we go to 10 gigabit, it's even faster, of course, 10 times faster. So, and then of course the type of switching or routing equipment also is a determinable factor, but it's less deterministic actually. What types do we have? We have most of these days in switches we have hardware-based systems. They employ switching fabrics which barely have any delay at all. So a packet comes in, the packet is examined where it has to go, and it's switched out the related port with basically no further delay if it's done as a switching fabric. It could also be done in software, most likely if there's a firewall or packet inspection or whatever involved, then it of course has more processing time, right? Because the software needs to examine the packet, needs to determine what to do with the packet and then forward it again. This is not deterministic anymore in most cases. And of course we have these mixed devices which have some hardware-based forwarding, but also with some soft processing in it. So we probably, if latency is of an issue, we need to know, do we have software-based packet forwarding or do we have hardware-based switching? Because that will make a difference as well. Now, and then there is some switching technology which is called store and forward. That's the standard forwarding technology. So a packet is being taken in by the switch and it's only forwarded once it's being received completely as a full packet. That's store and forward. That's the traditional forwarding technology. More advanced technology has what we call cut-through. So a switch can also, while it receives the first bits of a frame, which carry the destination information, it can also start to forward the data onto the output port with the risk of, well, not being able to transport the full packet, because if the full packet didn't ever arrive, it can't, forward anything. So it's an invalid transmission. But these are different technologies which are available. The standard technology is actually store and forward. That's what we have most times when we're looking at network technology. Now, then the next determining factor is the topology. Well, topology is very simple. The number of hops, I explained that earlier, contributes to latency. If we have 1 hop at gigabyte Ethernet, I explained it's 1 sample of delay. Well, if you have 7 or 8 of these hops, it's 7 or 8 samples. And just to remember, 4 hops at fast Ethernet. So if you just have 100 megabit Ethernet switches and have 4 of them in a row where you need to transport your packet through, it already comes up to 1 millisecond. Why am I mentioning the 1 millisecond? Well, because you will see later that somehow is the packet time of AES27 packets. So the analogy is a AES67 packet has the same originating latency as 4 fast Ethernet switches in a row. So there will be another millisecond of latency. The problem is that this is not a static delay. when we talk about packet forwarding, because the dynamic traffic situation on a network, on a particular network link, can add more latency. How's that? We will see later, because that's where quality of service comes into game. Now, beyond the number of hops, the speed of light, of course, also comes into game if we're talking distances. Wide area network application, of course. Again, here's the table with the distances. As you can see, no big deal as long as we stay within a facility, within a local area environment. But once we want to transport from New York to LA, we have at least 4,000 kilometers to cross apart, and that is a latency of 13.3 milliseconds, right? Speed of light. And we can't beat that. So whenever we want to transport something to California from here, we have another at least 13 milliseconds just due to the speed of light. And there, of course, are more factors in between as well. So we can't neglect the speed of light in certain applications. Again, fun fact. What fun fact? 1 millisecond, the mandatory AES22 packet time is just the same as 300 kilometers of transport. So I don't know exactly Washington, New York, is that about 300 kilometers? It's a bit more, I don't know. So again, every 300 kilometers, there's another AES67 packet time of latency involved. Okay, then these are all, things which are fairly easily to grab. What comes into a game with packet distribution, with networked media transport, is the network jitter or packet delay variation, PDV. What's that? Now, let's assume we have a transmitter who is sending out packets, in this case AES67 packets, so it's sending out a packet once per millisecond, right? Because it takes 1 millisecond to gather all the 48 samples at 48 kilohertz. Once it has that ready, it assembles the packet, sends it out, and then there's another millisecond of pause or wait time until the next 48 samples are there. So we have a frequency of about 1 millisecond transmit pace on the sender side. Now, the receiver is experienced, of course, the network transit delay, which may not be, significant at all if it's just one switch on a local network, but it might have, as we have seen, 13 milliseconds if we are transporting over to LA or even more, right? So the network transit delay in most cases can be seen as a static delay. It actually is not, but for this example here. And then what happens is, no, it's not this what happens. The packets are not coming in with 1 milliseconds pacing, because the network now is adding some weird thing, and that is the network jitter, the packet delay variation. That means that from the point of view of the receiver, packets are not coming in at 1 millisecond pacing, but sometimes they have 1.5 milliseconds or 0.9 milliseconds in between. So, and that is because packets receive, well, not constant forwarding throughout the network, and as you can see, that network jitter makes it not isochronous from the receiver point of view. So we have to cope with this. Network jitter, packet delay variation, needs to be taken into account. Switch performance, I mentioned that already. Hardware, software is also contributing to the packet delay variation. The hops, the routing in between, can also influence the packet delay variation, even if we have a change of speed from a gigabit or a fast Ethernet network, or maybe the other way around. That also may contribute to variation in the packet delays. It's a non-static thing here. And then the bandwidth utilization. Now, if I have a clean, empty network and I forward one packet or packets over one switch, I most likely see very little packet delay variation. But if I have lots of traffic on the network, like let's say there's a file copy going on, someone is recalling a big video file from the video server, that generates traffic. And the file server is able to dump lots of packets into the network, and then our transmitter wants to transmit a packet once in a while, every millisecond. Now, guess what? the outgoing link is crowded, it's overloaded, and those packets may have to wait for other packets just in front, for the video packets just in front of this packet. So that builds up packet delay variation. Here's a quick picture. If we have several flows coming in, that should go out to the same port. There's a queue on the egress port, right? And every packet has to line up and wait until the preceding packets have to be, have to be forwarded by the egress scheduler. So in this case, the packet number 6 just has to wait in a row before the other packets in front of him have to be forwarded, right? So that can build up additional packet delay variation. Now, the cure for this, and I have a complete different presentation which goes much more into the technical details, is quality of service. There's a standard mechanism which would allow us now to prioritize traffic. And this looks pretty much like this. Let's assume we have another number of flows coming into a particular switch, which should all go out to the same egress port. Let's say it's an uplink or whatever. Now, usually every switch has different priority queues. And we can prioritize particular traffic flows so that they go into the highest priority queue or in a higher priority queue than other traffic. So if we prioritize the scheme by having the video packets just traveling on best effort, so without any prioritization, but our audio packets with a higher priority, they go into a higher priority queue, and the egress scheduler is now looking before he starts transmission of the next packet, is there any packet waiting in the higher prioritized queue? So even if the lowest priority queue is filled up with all video packets, when there's one audio packet coming in into a higher queue, it gets prioritization and it will be forwarded as the next packet. Sounds all complicated, but you have seen that in practice, everyone, right? Remember this? That's exactly what quality of service is. Right? Some of you guys have the Premier Access or first class ticket, and they can go to the bridge whenever they show up at the gate, and all the others just have to wait. They have to line up, right? And that's what happens with our audio packets. They are traveling at least business class, right? And if not, there's a high probability that they build up some packet delay variation depending on how many people are waiting in the economy line. So that's quality of service, specifically differentiated services, which is a standard mechanism available on the network. Now, we still have a problem if we don't look for the bandwidth utilization on the egress port, because if we try to squeeze more prioritized traffic through a particular link than we have bandwidth, we still have a problem, because we can't accommodate all those business class passengers if the business class capacity is being filled up. So if we have competing traffic, that's what I mean with, other audio streams with the same priority, with the same high priority, it may result in a fully filled, in this case, middle priority queue, and then those packets again experience packet delay variation up to the point where they are even dropped. Because if the switch can't transport, the switch cannot transport more than the egress bandwidth link is providing, right? Well, and if we have more traffic to be transported than we have bandwidth, packets will even get dropped, even with quality of service in place. So it's always good to observe the available bandwidth. And as I said, this may cause overflow. There's a nice table I've prepared for this, which I can't call here in this presentation because it doesn't allow me to show the Excel table behind it. But just as you can see here, what's in the table, when usually on the gigabit network we have this, one sample forwarding delay per switch. When we have competing traffic, so I've assumed we have an 8-channel AES22 stream, the one we are observing, right? And on the same switch for the same egress port, we have 15 other streams with the same formatting. Now that can result in a worst case latency of what it is, 170 microseconds already, right? So if we have competing traffic with the same priority, that means we have observed delay variation, and There's a nice calculation which goes even down with further hops, and you can enter the number of competing streams in the setup, and it will give you an idea what can be the worst case latency a particular packet can experience on its way through the network. And of course that has to be accounted for later on, right? Which I will show in a minute. All right, so I can't pull this table, but that's it. So what's next? Well, the stream and packet configuration itself. With traditional audio, we have a sample, it's feed in, it's forwarded, and it's coming out of the system. It's not the case with packet transport anymore, because now it depends on the encoding parameters like sample rate, like the bit width of the PCM audio, the number of channels in a packet. This all determines the packet size at the end. And most important is what we call the packet time. I mentioned that earlier, a few minutes ago. The packet time determines how many frames of audio. Frames is the audio acronym for samples times channels, so how many samples or frames per packet at a given sample time, a sample rate should go into a packet. Again, AES22, 1 millisecond at 48 kilohertz means 48 samples. So the 1 millisecond times means we have packets with 48 frames, to be correct, per packet. That means that packet is ready 1 millisecond after the initial sample arrived or is being sampled. But it can't go out before all the 48 samples have been gathered. So the packet time is a determining factor with the latency. If we lower the packet time, let's say we are just gathering 16 samples, it's 333 microseconds, right? And some solutions even offer packet times of 1 frame. Well, you wouldn't send a packet with just, 1 channel and 1 frame in it, because that's 24 bytes of 24 bits, 3 bytes of payload data, with another, 40 bytes of header data in the RGP, UDP, IP, Ethernet, blah blah blah. But if you have a MADI stream, 64 channels with 4 bytes AES3 format in it, right? Then it's reasonable to send that out with just 1 frame in it, if your hardware does support this, right? So you can have low latencies with respect to the packet time, but AES67 again is mandating for async. So this is what I just described. It's just a picture behind it. We have the frames. We have the stream of frames, and of course the number of frames determines at the end what the packet time is. Here's another nice table which I can't display in detail as well. But if you look at the number of frames per packet at 48 kilohertz, 48, that's the 1 millisecond time, and that is the originating latency we can't beat. So at 1 millisecond packet time, we always will have a latency of a minimum of 1 millisecond, regardless how long the packets have to travel, how many hops, how many competing traffic. We can't get below 1 millisecond unless we reduce the packet time, right? That's the idea behind this table. And moving on, then another contributing factor to latency is the sender and receiver implementation. I just mentioned that. If your sender is based on hardware or embedded solution or software, it will have a different additional latency which you have to account for. How's that? Well, if you have a hardware implementation with an FPGA, like the COM-IMX we have developed, it has quite a high number of audio channels being able to be processed by the board. It can support high sample rates and even most interesting, lowest latency support of down to 1 sample per packet. That doesn't mean anything else than packets can be sent out with just 1 audio frame in it. Again, you wouldn't do that for a single channel audio, but you would use it for MADI packet size, right? So if you have a MADI channel coming in and the board can process MADI, you can throw out a packet every MADI frame, just 1 frame. And that's the lowest possible packetization latency you can get to. Well, that has also redundancy in it and so on, blah, blah, blah. We have other solutions from other partners on the chip. It's not just boards, but also on the chip, who have very low latencies. And then we have those virtual sound cards on the other end of the scale, pure software implementations. Now, available from Lavo merging, ALC networks, H7R. We know our friends from TELUS have virtual sound cards available as well. And here, the operating system comes into game itself. Now, what's the operating system? Well, if you want to send out a packet, you nicely packetize your samples, right? And then throw it to the IP stack. But the IP stack is not under your control. It's under control of the operating system. So, and whenever the operating system thinks, okay, I'm now ready to send off this packet, it does this, but it's not deterministic anymore. So, and that at the end accounts for another typical processing latency, which can go up as high as 10 milliseconds. So that means the receiver may encounter that the latency seen upon incoming intake of a packet may be as huge as 10 milliseconds because of the additional processing and software, software variation, software interrupt variation in the operating system. The further down you go to hardware, the more control you have on the hardware side of things, the less software jitter we will have in a particular packet stream. So this is another factor which you need to take in mind. If you're sending off something with a virtual sound card, your receiver needs to have a larger receive buffer to cope with the possible software jitter. So, and then finally, there's one factor which is a very important one and a very useful one on the other hand. Well, all the others are not so useful. This one is a very useful factor. It's the stream alignment, right? So the idea is, if we have a typical, let's say, production chain, we have video originating from the camera, the video is passed through 2 processing stages and it's finally displayed on a display, just as an example. We also have an audio stream sampled via a microphone, then it passes through one processing device and it's destined to be played out on a loudspeaker. Most likely, the audio stream will arrive at the speaker before the video, the related video frame will arrive at the video display, right? And with the involvement of reference clock and PTP, which I explained yesterday and will also explain later on in the afternoon again, we now have means of aligning these streams. So what we essentially have to do, we have to tell the loudspeaker to hold off play out until the matching video frame has arrived at the video display. And that is the task of a broadcast control system, which is basically telling the devices when to play out a particular frame in order to align it to other incoming streams. Now, that's something which I want to explain a bit more, yeah. This is called the link offset. We have a nice diagram in AES22 which explains the overall, the total thing with this link offset and the receive buffer. So this is a scheme of a typical AES22 implementation, and it's very similar to SMPTE 2110 as well. We have a sender device, we have a receiver device, we have an IP network in between, and here's the ingress time reference point. That's exactly the time when a particular sample is ingested at the sender. That's our reference plane. At this point in time, it receives a particular timestamp. And on the other side, we have the reference plane at the receiver. That's the plane where it's forwarding the packet, or well, the sample, not the packet, the sample to the output stage, right? So what actually, how this relates to each other is we have a timestamp with the first sample, which is transported inside the RTP packet. We have a chosen link offset, and the link offset needs also to take into account a potential random RTP offset. That's what I explained yesterday. And then, through this calculation, we have the desired playout time for the particular sample at the receiver side. So by telling a receiver the desired link offset, it exactly knows when to play out a particular sample. And by doing this across the whole system between all streams which potentially should be aligned, we have a perfectly aligned playout in our network system, even at different devices on the network. So link offset is the important thing to recall, and with link offset, just as I had with the example with the loudspeaker, the receive packet buffer is vital and important, the size of it. Now, if we go back to our initial diagram of those packets, evenly spaced at the transmitter, not evenly spaced when they are received, we see that the largest packet jitter is between packet 4 and 5, or with respect to the originating time of packet 5 is here. So the receiver, taking this jitter into account, has to calculate the playout by accounting for the maximum experienced network jitter, which is apparently this part here. And then that's where it can, then also the alignment of, inter-alignment of streams comes into game, and that's the whole link offset explanation. And so we have this link offset between the first sample going or being sampled from by the transmitter before we can actually play out the first sample at the receiver. So the link offset is vital by telling the receiver when to play out a particular sample, and then of course the receiver can nicely isochronously play out the samples as they have been acquired by the particular transmitter. Okay, final example. We had a global AES67 over WAN demo. Yes, AES67 over wide area networking. So we had 2 continents, we had 3 sites, 4 sites, one in Ottawa, in Germany, Mittweida, Grenoble, France, Lausanne, Switzerland. We were using gear from Ross, direct out and merging there, and we are utilizing the Amazon cloud. How can we transport AES67 through the cloud? Well, Amazon doesn't understand any AES67 at all, right? But we can encapsulate the AES67 traffic in, other IP packets, and then after receiving them, send them forward as AES67 traffic to the individual devices. And we did this by employing SRT codecs. So what we did, we were feeding the AES67 packets into an SRT encoder, which copes for packet loss and all these kind of things on its way through the Amazon cloud. And on the other side, there was an SRT decoder who nicely unpacks the AES67 traffic again and then forwards it to the individual devices. And now, how's the synchronization done? We didn't transport PTP, it would be of no use at all, but we used the almighty referencer buffers. So all of these sites had their local GPS reference grandmasters. And with that, we had a perfect time synchronization. The timestamps still are in the AES67 packets. We only had to tell the devices to respect any build-up latency, which is the packet delay variation, the static transport delay across the distance, and those things which which are also being added by the SRT, because SRT copes for packet loss, right? So we had to calculate a longer delay to also cope with the SRT characteristics. So here's the summary of that: synchronization via GPS on local sites. There is packet loss, but that's managed by SRT. So if we have a packet loss through the Amazon cloud, it can be resent, and SRT is making sure that all the packets are nicely arranged on the other side of things. And the resulting end-to-end latency is somewhat between 200 to 600 milliseconds, depending on various factors, of course. So at the end, we have to tell the AES67 receivers that they have to delay the playout with respect to the original timestamps, which are still in the AES67 packets, by, let's say, 600 or 500 or whatever the experience delay was milliseconds. That doesn't mean that the receive buffer actually had to have this size, because there's a lot of delay in between already being covered, but you sure can't go with a receive buffer of just 3 milliseconds or 10 milliseconds, right? So deep buffer receive buffers are actually key for making wide area network transport of AES67 possible. But it worked out. And so as a summary, the determining factors for latency are the network technology, the topology, the network jitter, stream and packet configuration, sender receiver implementation, and then the useful stream alignment. All this needs to be taken into account, and that sounds like we have ugly 20 milliseconds plus of latency in all our networks, right? No, we don't have that, because link offset receiver buffer size, we can have sub-millisecond latencies, well, if the network plays nicely with us. So if you have a small local environment and not much competing traffic and QoS properly in place and everything done, we can transport MADI-like IP streams through the network with MADI-like latencies, right? But if you use large corporate networks with larger packet times and even wide area network transfers in between, we have to deal with the resulting latencies coming off from all these different factors, and have set a suitable link offset, which also requires that the receiver most likely will have a suitable receiver size to cope with the network jitter being experienced. Right? Again, keep in mind, the receiver buffer size a device offers has nothing to do with the actual link offset being used. A device which offers a huge receiver buffer can still work with very, very small link offsets, but has the capability to accommodate very much of the network jitter or packet delay variation built up through the transport through the network. So that's it. No time for questions, I think. Yeah. Oh, yeah. Right. Since you have so many people here, the presentations will be online. If you want to receive a copy, just make sure that Tina registers your QR code on the badge. And as always, we have a nice collection of resources available on the Ravenna website, as well as on the AIMS website. And if you have anything you want to ask me directly, just shoot me a mail at ravenna.alcnetworks.de. Okay. That's it. You reached the end of the presentation, even with a 6-minute delay of the flight.
No problem. Thank you very much, Andreas. That was very interesting. So we're going to move straight on to our next presentation now. And by the way, just to mention, we do have headphones at the back. If anybody's having trouble hearing in this noisy environment, grab yourself some headphones. Next up, we have Patrick Kalani from Audinate, and he's going to talk about designing systems combining Dante with open standards like AES22 and SMPTE SD2110.